because the pipe itself, when you type it on the terminal, actually it's called a system call called pipe to create it. And when it creates, it's a piece of memory plus some special control. So what is the special control over the pipe? And you can see that the pipe is actually what we call a bound buffer, bound queue, a queue with a maximum size that you cannot go beyond that. In writing queue data structure, in data structure course, you will know that, okay, I have to take care about the length or the size of the queue. When the size is full, I have to specially handle it. And in data structure course, never told you what you have to do, okay? But in OS course, we cannot, let's say some people already answered me in the last lecture that, hey, if I have an enqueue system call, now this type of system call now is converted from write in order to enqueue it, so I consider it as a part of the kernel. When you do the enqueue and you find that the queue is full, now in case for the pipe is not the router, you cannot have a drop tail treatment. Okay, you cannot drop the tail and say that, okay, I dropped the packet. In kernel, it's not. You cannot lose anything, okay, inside an operating system. So what should this guy do? So this guy is a process called ls. Ls supposed to be standing there and wait for the availability of the free space, okay? So it's no longer a free space, so I have to stop. What's the meaning of stop? You can treat it as receiving a suspension signal. Then this guy will be suspended. Now, how can this guy be active again? So be active again is then the partner. The partner is the other end of the queue. In the other end of the queue will correspondingly call, not enqueue this time, but dequeue. You will dequeue something from the queue, from the head of it, so that you will have an effect that whenever the ls writes something, let's say hello world, hello, maybe hello is easier to describe, okay? Hello, only 5 characters. Then the first time you enqueue is H character and then ELLO. So when the dequeue point will also get in the same order out. Now when the dequeue is happening, you will have more control, okay? Not just about the size, but about his partner. So his partner is originally, I don't know what the status may be, it is being blocked because of the enqueue system, the kernel part enqueue has found some problem. So you have the responsibility to wake him up by saying, let's say, continuous signal. Then this guy will continue to run, okay? So this is a high-level description of what we call the producer-consumer model. Very, very common in writing network program, as well as some multi-threading, we call it a multi-threading paradigm. Okay, so the multi-threading paradigm contains more than one model. This is called producer-consumer model. Now, I will give you another model, which is not very commonly used, okay? What is that? It's parallel sorting, okay? So what is the meaning of parallel sorting? Now, it's the time to record your memory over quick sort, okay? So what is quick sort? Yeah, at least you have 2 steps, okay? One is before the recursion. One is now you have to do recursion. Now, what is the time that you start the quick sort? Of course, is after you read what happened here. If you have turn down the volume. Okay, better. So what is the time? The time is when you load all the data, into the process. Let's say the process is called a parent process. So when you load data and you keep it in an array, okay, then what you're going to do next, I don't know whether you're calling a library call for sorting or you're writing your data structure or algorithm assignment so that you have to write the quick sort by yourself, but it will include one very important operation is to find supposed to be a middle point, okay? Well, but you know it's not always that lucky. Now, suppose there's a middle point, then we call it P, and then you will swap the data inside the array so that the first half is containing data smaller than P and or smaller than equal, okay? The second half or the later half is greater than equal to P. Now this is the quick sort, right? And the second half of the quick sort is doing recursion. You are doing the same thing in here. Okay, so what we are focusing is not about rearranging the data, but after the rearrangement of data, we have 2 halves. Why not we do a fork? Yeah, What is the meaning? We do a fork over this region, or I should say that it's not about region. Fork is about whole memory as well as the program. So when I do a fork, I have to control that. Okay, it's after I put the two data in two different regions, then I call fork, and inside the child process, this guy focus on the left-hand side. This guy focus on the right-hand side, and it will do the same quick sort. Okay. Now imagine that if this is doable. Now there's several technical hurdles there. Now first technical hurdle is how can these two guys share the same piece of data? If you're working on memory, that's easy because you're doing fork, and the memory is duplicated into from parent to child. So the memory sharing before the fork and after the fork is nicely done. Okay. Another technical hurdle is after you're doing the fork, how can you combine things together? Okay. So maybe you have to use your imagination. Let's say that we write data to a file. Okay. Write data to a file so that you can have a centralized place to hold the data. Then you have to merge the data by using fwrite, okay, or printf, okay. Now here is the time that you will gain something. So what is the meaning of gain something? Actually, you are allowing two CPU at a time, okay. If you have two CPU at a time to do a sorting, okay. So why I said it's not common model, okay. Why it's not common model? Because when you do a sorting like this, okay, you are actually, how can I describe it? You are having the same machine, okay, and sort the data over the same machine, okay? The common model is not having it in the same machine, but split the data across different machines, okay? So if you're interested in, there are models in doing so. Of course, you can use networking. We use socket, okay, or not just using socket. Very recent, okay, our department, the CSCI department, as well as the physics department, has joined a competition called, what's the name? I did that once, okay. I was the coach in a 2013. It's called Asia Supercomputing Challenge, something like that, okay. Yeah, we supposed to get a place for 7, okay, across the whole China, supposed to be 7, okay, but not very good. I consider it's a bad result. So we are using this model, okay. So this model is communicating with different CPUs as well as different machines, okay. So of course we are not using the networking socket programming stuff. We are using some library called message passing interface (MPI). Okay, or you will heard of something called if you're standing at the edge of computing, something called OpenMP, OpenCL, something like that. Okay, so it's about how to distribute data across a network of computers or more than one CPU. Okay, so in our model in operating system, we cannot go that far. Okay, we only have one machine to control, let's say, okay? So we have to use another model. Another model means using a shared object. As in previous illustration, we have a shared object. There's a shared memory, a piece of memory shared across the two processes. When I do a fork, okay, then I can share it. Or you will have a shared object just like a file. Okay, I open a file. When I open a file, as I described in the beginning of this chapter, you will be able to read and write from the same file without any problem, even though you have more than one process have opened it. Okay, so then this is another model in computing, in doing some parallel stuff. Okay, so this is the parallel computing basics. Okay, parallel computing basics is not that easy. Okay, if you have interest in it, okay, our department won't available having this course, okay? You may have to take some Coursera courses. Coursera, you know Coursera? No? No one knows? Yeah, someone knows, okay? Some Coursera courses talk about how to make use of GPU, make use of multiple CPU, okay? I've taken one quite good, okay? It's from UIUC, okay? So, then, well, it seems that we have some technical hurdles, but we have some solution already, okay? Some solution is above the pipe, which is available from the kernel. I just call a system call, and then I get this facility done. Good. Now, another problem is about when you have something not provided by the kernel. Let's say I'm not using a pipe, okay? I use a file. I said that the file don't allow any control over or whether you're locking a file for the writer or locking a file for the reader, okay? We don't have such a control. So then we have some problem, okay? And this problem is very interesting. We call it a race condition, just like two process racing for some resource, okay? When one is wins the match, okay, then he will get something. And for someone lost, okay, he may do something bad. Now, let's see what is the scenario or the motivation. The motivation is we have so many objects here. So the first object is I go through the file. Okay, the file we know that you can open it at the same time. Now, what is the meaning of shared memory? So shared memory, you can find it here. So this is my Linux. When you do a Linux, you can call a command called, let me scroll down a bit. Okay. So called IPCS. So what is IPCS? Inter-process communication resource or resource status. Okay, it's the S for status. Okay. So let's take a look at what are the resources available in the system for IPC. So when I type enter, some very good name appear, like a message queue, okay? So we can implement a queue over two processes, and this is a delivery of some messages which is shared across processes. But you see, when I start up this system, no processes is using this message queue. So one of the things that are being used a lot is something upper here. So well, what are the names here? Let's go. Yeah, we found it. The name is called shared memory. Okay, so this is some pieces of memory that being created in the system, and the system means the kernel. The kernel allow different process to attach to it. Okay, so you will see this column is the why run out of memory, run out of battery. So okay, yeah. This guy sucks. Okay. So this is the number of attachment. So you will see how many processes attached to this piece of memory. Okay. Every row is a piece of memory. Okay. For the items, these two guys you don't understand. Okay. Don't worry. This guy means that this is my Ubuntu account created. Permission. Who can access this memory? How large is this memory? Whether it is something that is a destination, I don't know what is that. Okay, yeah. I supposed to be the tutor of the OS course. Okay, maybe you have heard of it. Okay, several years ago, I was a TA. Okay, even now there is a professor coming back to teach in CSCI. I was his tutor. Okay, yes, kind of stuck. Okay, he was a professor, now I'm a lecturer. Okay, that's fine. So that's fine. I'm okay with that. Okay. I teach them. While I teach them, we in the curriculum we have this kind of programming. Okay, and I tell you that you need a good book in order to learn how to write shared memory. So I choose to skip it. Okay, because that book is very old already. All of the things are already outdated. Nowadays we don't use shared memory, but use multi-threading model. Okay, so that's why why I have a message just coming in. Okay, that's why in a course schedule, after talking about this chapter, okay, this chapter is IPC. Okay, we will go to threading, so that we will use all the things learned from part 5 and apply it in part 6. Because part 6, the multi-threading allows something can be done very easily. So what is done being very easily is the creation of a shared memory. Okay? So keep in your mind there are some memories that can be created. Now, from a kernel point of view, the pipe, okay, is correctly done. Okay, it's correctly done. There is no anyone can break its implementation. Okay, but there is some restriction. The restriction is The pipe has a left end and a right end, right? The left end must be one process. The right end must be another process. So at most, there are only two players for pipes, okay? Now, how about I want to implement something that allows multiple processes to write to and multiple processes to read from, okay? So there are tons of applications, particularly in processing in an inside network. Let's say you're emulating a software router. Then it's definitely needed that there is a multiple data stream coming into your software router, and you need a producer-consumer model to hold all the data that is coming in and implement a queue, no matter whether you're using a dovetail, early random detection, so on and so forth. Then you have to consume it in the other end. Now, what is consumption may be more than one socket or one process. So you will have multiple process in, multiple process out, and which is not available in the kernel. You have to write it yourself, okay? So, of course, the shared memory as well as the file, you have to write the protection by yourself. Now, we're talking about how to write protection. And first, we have to understand that there is a potential problem in having resources that is available to the user, and the hustle is called, there's a problem, there's a hustle. It's called a race condition, and race condition is happen not over high-level programming language. You cannot see it, okay? Usually when we talk about this kind of problem is having two concerns. One is, of course, we have multiple processes raising for one resource. If we have one process only, no problem. Okay, multiple processes going to one resource. Let's say the resource is shared memory holding a value 10, let's say. Now, we have two processes. One is gonna have an addition over it, having an add 10. Another is a minus 10 from it. So you expect that for no matter how the execution happens, you will have the ending result of the shared memory keep constant to be 10, right? When it's add, when it's minus, huh? It seems to be okay. But in CPU execution, it's not the case. CPU execution, we have something bad happen. What is the bad thing is we don't have operations that can do the addition, or I should say break it into pieces, okay? Loading the memory from the share part to your process part. First load it in to your process, and then you update the image inside or the value inside the process, then you load it back to the shared memory. These three steps, there is no way, or I should say there are ways, but it's not easily implemented, okay? If you look at it in a simplest form, there are three different steps, okay? The best thing is we want these three guys to execute in a row, okay? Don't interrupt it, okay? Once I start 2.1, I hope that 2.2 and 2.3 will execute continuously without any interruption. But, well, computer system is not only owned by one process, it will owned by different processes, so interruption happens. So this is the case requirement number 2. We have interruption. Okay, we have more than one process raising for a particular piece of data or shared object. Requirement number 2, we have interruption. Okay, although third requirement is don't have any protection over this guy. So what will happen? Okay, so there are animations. So the animation is easy. We start with something normal, very easy way to understand it. First, I have a shared memory here. The two pieces of code are very similar, except 2.2. The line 2.2, one is add, one is minus. Okay, so we need to do is loading something from the memory. I should say that you're loading it into the register. Okay, loading it from register, and the register are temporarily owned by particular process A or B, no problem. Okay, and after you load it in, you modify the image inside the register, and you load it back to the shared memory. And that is a common practice when you learn about assembly language. If you didn't know about assembly language, I tell you this is working in a back box called CPU. Okay, CPU is doing something like that. Now, let's go with a normal flow. The normal flow is like this. The first line of execution will be 2.1 on process A. So what happened to it? boom, 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 sound. Okay, so the process A start first. The good execution will be 1, 2. What happened? Hello. 1, 2, 3, all execute in a row. Okay, then you will change the data from 10 to 20. Easy. Now, another execution start will be the process B. So before I have the process B running, okay, I have a status of the process A to be running, then this guy is ready. Now we have context switching. So when the context switching comes in, you will have to change to another process. Let's say we choose process B, and it will execute 1, 2, 3, so on and so forth. Okay? So this execution sequence is something which we want, and a desirable. What happened to this guy? Okay? Huh? Is you know what happened? Yeah, it seems to be it. I didn't wear anything that will interrupt it. Strange. Okay, so this is normal flow. Now we will show the. I know, running out of battery. Yes, always me. Okay, I don't know why. It's always me. Okay, yeah. Oh, no. Good. It's always me draining out all the battery, not just this room I count. ELB, LT, TY, LT, all being a container made by me. Okay? I don't know why. Every time I stand there, the battery will drain out. Okay, so yeah, maybe I exert too many power over it. Okay? No, continue. So this is the bad move. Good move, sorry, good move. Now how about a bad move? Bad move can be something like this. Let's say that is execution from number 2. Okay? Bad move. 211 of process A start first. Now you have the memory 10 loaded in register A, no problem. Now we have context switching. So what is the meaning of context switching? Although the two code say that you have to load the data into the register A, but don't forget that whenever we have context switching, the register for a particular process will be back up first. Okay, back up. So that means that this register A for process A, okay, will be saved before I load back for the image for process B. So it's as if, although we have the same register name, we have 2 different copies. Okay? So when I have the context switching again, then this guy will also load the same thing in. Now, don't think that, yeah, you just create a false scenario. No. Why it's not a false scenario? Think about it. What happened if the whole picture, now I change it in network programming? This time it's not loading memory X to register A, but loading a remote variable from a server, from a database, and load it through a short socket. Then you will experience some time. And this is the moment that you will probably have context switching from another process, maybe even in other machine. Okay, so this model is scalable from same CPU scenario to a cross-network scenario. So let me continue. So when you look at this, you will already find something wrong. Why? Because both processes load the value 10. Okay? Then no matter what it does next, let's say the 3 and 4 step will be something like this. Yeah, it doesn't matter. Doesn't matter. Because why? Their local copies now become different. One is 0, one is 20. Right? This guy is 20, one is 0. Now, what can you say about the final value of shared memory? Yeah, pretty bad, huh? Pretty bad, huh? Can you say anything about it? Yeah, you can say something. It's no matter how the executions ends, I don't care whether this is 1, 3, 2, 4, then this 2.3 of process A or process B, we will have wrong results. Okay? No matter what, it's not keeping the value constant, even though I have one process updated with addition, one is subtraction with the same amount. So this is something really bad, and I don't think that this is a wrong implementation, first of all. Okay, you can scale it up to the networking scenario, database scenario, then you will find it applicable. Okay, I can tell you that usually means 99% of the execution sequence will always be fine. So that when you write your program, okay, in a control environment means that it's very few loading, no real traffic coming in, then usually you will have execution normal, 99%, and the 1% of it is problematic. Okay, so I experienced that. Okay, it's not me, but my FYP student. Okay, they're really using this kind of control over the database. Okay, but they implemented it in the wrong place. Okay, they attend this lecture and they know that, oh, we have something wrong. Okay, so my FYP student are writing applications, writing data to database. Okay, and they call the wrong function so that there is no protection. Okay, and whenever they do their demonstration to me, that's fine. When they do a demonstration over an FYP marker, yeah, it goes wrong. Okay, and they just stunned it there. Huh? What happened? Okay, I said, yeah, maybe race condition. Yeah, we started. Okay, then after we started, no problem. Okay, so that is the case for the 99%. Is that this is fine. Okay, some people will argue that, hey, we can always patch this scenario. How? Okay, yeah, they will say that, yeah, maybe before 2.1 we add a sleep there. Do you understand what I mean? Yeah, let's say this process has sleep, this process don't have sleep, okay? Then, yeah, this guy is running always faster than the B, but the one with sleep is slower, the one with no sleep is faster, okay? You are not solving the problem, come on, okay? So you are just hiding there. So, oh yeah, will be a problem. So let's do a sleep so that we let the user to see that, yeah, we're running something, okay? Yeah. And you understand that it's 1 second delay, they will think that, we need something execution, okay? Yeah, which is not solving the problem. I don't like it, okay? So in case that, although we don't have such an assignment, but I think that you use multi-threading a lot, and particularly when you write a program. So hope that you will not try to solve the problem using sleep, or someone not just do sleep, okay? They just pretended they're multi-threading, okay? It's actually no threading, okay? I don't know how they do it, okay? They just send me the code and have some problem and say, hey, where is your thread? Yeah, they say that, thread is dangerous, okay? We don't implement it. Okay. I know they're dangerous, so that's why you have to solve it, okay? Yes, and what is the problem here? The problem has a name. Race condition. It's very strange. Why it's called race condition? It's not something like a real car racing. The car racing is the fastest car win. Okay? It's not the fastest car wins here. It's the slowest car win. Understand what I mean? Take a look here. When you want to save your value to the shared memory, do you want to be the fastest car? No. You want to be the slowest one. Okay? So, yeah, but again, I don't want to tweet a bit over the race condition. I don't want to change the name. Okay? Every book calls it race condition. The definition of a race condition is the execution sequence really defines the results, which should not be like that, right? You have a normal system, okay? You know that there are multiple processes running, okay? Suppose that no matter how the system react to the different process execution, they should give you the same results. But no, okay? If you don't have any protection, we will have this kind of problem. And how to solve this problem? There are many controls, okay? The one control I've told you is about sleeping, okay? People suggest that, sleep before executing it, okay? Or even some controls say that, maybe we start this thread first, and then this thread dies, and start this thread, okay? Yeah, you're not solving problem, okay? So some other control is we have to achieve something, okay? So the achievement of what? The scenario compound, it's mutual exclusion. So what's the mutual exclusion? Mutual exclusion means that when you're executing something, you are not allowed to do it. Okay, not allowed doesn't mean that you go to sleep, okay? But there is a control inside the system that a system of processes, okay, not inside the kernel, okay? System of processes, this allow you to go on. And to draw it as a picture is something like this. When I start to load, okay, start to load data from the shared memory, okay? So we have 3 steps, remember? The loading, the update, and real write, okay? Not just the writing step, but all 3 steps. Once I start the first step, I will lock down the entire shared memory so that another process want to access, you will be stopped from doing so. Okay? So this kind of control is very common. Okay? Like the database stuff I talked about when I start this chapter. What is database stuff? Let's say that you have a table. Okay? How many of you don't know database stuff? Yeah. Okay, so everybody knows. So you have a table, okay? The table has some rows, okay? We particularly love one of the rows, okay? Then some process want to write to it, some process want to read. So whenever you have different reader, no problem, just let them read, okay? But whenever we have a writer, that partial writer, let's say this is a writer, process A, want to write to the shared memory, another writer or even reader should be blocked, right? This kind of concept is very clear. And, well, how to implement it is the problem, right? So to implement it, in terms of coding, okay? So we have to set up some region, okay? So what is the region? We usually call it critical section or critical region. So the critical region, you usually have some control over it. Let's say you have what we call the entry section of the entry. Entry of section. What happened to me? Okay. Entry of the section. Okay, so I color it in the red because it's very important. You cannot miss it. Okay, so this is our color scheme. Okay, now from this slide onwards, I'll use this coloring scheme. The coloring scheme is the pink part is the critical section. The red guy is the entry. The green guy is the exit. Okay, so how can you set up such a critical section? Is by you. Okay, you define which code is important, then you put it inside this region. Okay, and the region including instruction in reading the shared behind the shared object. Okay, so you include a statement that read the object or write to the objects. Okay, so then you set it up. Now, maybe this is not enough for you to understand. Okay, so I think this figure will be more easier for you to understand. So what is this scenario? The scenario is an outside toilet. Okay? So this scenario is like this. You are a process. Okay? So when you stand in front of the toilet door, okay, you find that it's not locked. Okay? So it's not locked. It's called vacant. Okay? It's green. Okay? In our engineering building, it's white. Okay? I don't know for a case for the female toilet. Okay? For the case for male toilet, it's white. Okay? Then you go in, okay? So what is the code here? The code here is, and why I cannot change this? What happened to my remote? Okay, okay, come on. Yeah, it's just stop. It just don't move. Wait for a moment. Is it because I have a really bad system here? Oh, okay, no problem. It's moving now. Okay. So what is the code? The code is the red guy. Okay. The red guy. The red guy is actually a lock. Okay. Or the action that work with the lock. So when you enter the toilet, okay, you are going in and then lock. Okay. Yeah, you won't find it there in case that there's lock and no people in there. Okay. Yeah. Or someone go in there without lock. Okay. And that guy will pay his penalty. Okay. If he forget to lock and then go in. Okay, I experienced many times. Like, I don't know why, okay, in a male version, okay, is even though I lock it, someone attempt to open it. Okay, very horrible. Okay, so and yeah, so you can think of it the case that I lock it and I forget to lock it and someone attempt to open it, then we will have a race condition. Okay, racing for the toilet seat. Okay, very dangerous. Okay, so now when you go in. You execute your critical section. Remember, whenever you go in, you're supposed to be doing something critical. Yeah, you won't do any other non-critical stuff inside the set. Huh? So after you finish all the critical stuff, okay, you do the cleanup. I don't know what is the cleanup, okay, but including one very important step. The cleanup is including the green part, okay. The green part is about unlock, okay. So you unlock and go out of the section, and the transaction done. Very transaction done. Now, how about other people? Other people are just other processes. And when they try to go into that section, okay, means that they will, means that they will execute this red guy. Now for them, the red guy actually is a signal. When it's vacant, you go in. If it's occupied, then you cannot go in, right? So what did they do, okay? They will be blocked, okay? They will be suspended, okay? So suspended just standing here, okay, in real world, okay, we will have a queue, okay, and in a process world, maybe we have a queue, maybe we don't have, okay, it just depends on the implementation, okay. So let's imagine that there is no queue, okay. So whenever a process goes in front of the toilet resource, okay, we'll find that, oh, vacant, go in. Oh, it is occupied, then I'm blocked, standing outside. Now, when I turn the lock, actually it's a very interesting stuff. When I turn the lock, it's actually a broadcast signal. Yeah, broadcast. Broadcast to everyone who's looking at it. Ah, that guy is coming out. Okay, so I can really raise. That is a really raise. Okay, to raise several processes want to go into the toilet. Okay. Now, of course, there are some restriction over the resource. That is the toilet 6. Okay, so I didn't say anything about it. Now, first of all, which is very easily understandable in this scenario is that process only allow one process to update it, right? And you won't expect 2 people in there. Yeah, only one. Okay. So which is also true for computer system. Whenever we have a resource, you want to update it, we're only allowed one process to update it. So that's why I find that this example is perfect. Okay, perfect in explaining everything in the computer world. Okay, yeah, something that is really critical inside there. You only have one user using it. Okay, and one more thing. This example allows me to elaborate more examples. Like inside there, you have different kind of resources. Okay, when you collect enough items, then you go in. What is the meaning? You go in. We want to go inside, but you cannot find any toilet paper there. Will you start your process? No, you won't start, right? So you have to collect enough resources before you start, okay? But so happen that what happens if other people holding their resources? Yeah, and I'm standing just outside the seat, okay? You are holding the toilet paper, okay? So what should we do? Okay, we both block there. Okay, no, you don't choose both to be blocked there, right? You will try to release both resource, okay? Yeah, either one of you will release the resource, okay? So maybe we do a fair game, okay? Let's release the resource together, okay? And you raise the both resources together again, okay? Yeah, this is really happening in the process world, okay? But in the real world, okay, usually we can negotiate, okay? So if you're more urgent, okay, you go first, okay? I'm not that urgent, okay? I find another CPU, okay? Yeah, I find another floor, I go to another floor, okay? Yeah, this is a very good scenario that we can explain many things. Just use toilet, people sit in the toilet doing transaction, and finish it, go out, and can explain this diagram. Okay, so after this diagram, I don't think that for those who skip the lesson, I don't care. Okay, for those sitting here, you will understand. Okay, now, so for short summary, mutual exclusion, okay, is the goal. Okay, so don't mix up the vocabulary. Okay, mutual exclusion is the goal. Okay, and in the toilet set, we have a perfect solution. Okay, as long as the door lock works. Okay, if the door locks jam or it's just fail, okay, it's another problem. Okay, and race collision is a problem. So the race collision is also well defined in the real world. Okay, you really race to that resource. Okay, so this is the 2 new vocabulary to you guys. And in defining, okay, the critical section, now there is something extra, but also both applicable to the real world case, okay? So the definition of the critical section must be as tight as possible. So what is the meaning, okay? That means that you use the resource and you have to be good to others. Don't put all bunch of, let's say, including, I don't know why someone will bring the laptop into the toilet, okay? Yeah, do you see that? Yeah, I see many. When iPad was a new toy, okay, some people will bring the iPad. When iPhone is new toy, then bring iPhone, okay? Yeah, then go in the toilet and do the critical section, okay? But there's not critical stuff, right? You can play your iPad in your office, okay, or in the lab, okay? Don't play iPad inside the toilet. So you have to make as few as operations, keep as few as operations inside the critical section, okay? So there's some requirement. Also, I have explained to you that there may be more than one resource that you gain before you start the critical section, okay? So implementing this, the entry and the exit is a challenge, okay? So there's another vocabulary. This time, the lock and unlock. How can we implement them? So are there some objects that help me to unlock, or some codes that we can borrow from the kernel or implement it as a system call? We will go through it, okay, in tomorrow class, okay? One more important stuff is this sentence explain why we have there is a question in the first week, okay? The question in the first week is I asked it in this following style. When you buy a CPU, okay, buy a machines, okay, the sales tell you that, hey, this CPU is let's say 2 gigahertz, okay, I don't know this, I don't know whether this exists or not, but I just made a random number. 2 gigahertz, 2 cores. Another CPU, 2 gigahertz, 4 cores, okay? And the sales keep on saying that, yeah, the 4 core is better, okay? Twice as fast as the 2 core, which is not, okay? You understand? It is not, but it's only by experience, okay? The real life experience telling you that the 4 core system is not twice as fast as the 2 core system. Now we have the why. We have the what part of the reason. Part of the reason is whenever you have multiple processes execute together, and when they want to produce something meaningful, when they work together, it may sometimes ask other people to block so that we can keep some resources only owned by one guy, okay? Now this time it's not about a CPU problem, it's about a resource problem. You cannot just put many CPU, many RAM there. Is about the application. The application only have one resource. No matter how many processes you have, no matter how many CPUs you have, you cannot speed it up just because mutual exclusion. Okay, so there's one reason. Another reason, of course, is some part of our system is not written in a parallel way. Let's say as long as now, okay, the kernel is not running in a parallel way. Okay, it's just only one kernel. Okay, we don't have distributed version over distributed environment. Okay, so next lecture we're going to talk about how to implement the lock, the door exit. Okay, and then we will keep on telling you something more, like how to achieve the goal if we have more resources that we have to own before we start. Okay, and then we will. I hope that tomorrow you will come earlier, okay, or stay awake. See, we have so many codes here, okay, and then we will talk about classic models, okay. I don't think that we have enough time to cover classic model. Classic model, first classic model is producer consumer, how there are multiple processes as producer and multiple consumer. Then we have the second, so many codes you can see it, okay. Second is called dining philosopher. Dining philosopher is a game actually. You have a course row, okay, a row with many entries, okay. How can you guarantee that the traffic won't get jammed, okay? So if you want a diagram, I can show you last semester final exam paper, okay? So last year final exam paper have a very horrible stuff. Those people want to kill me. Wait. Okay, so let's take a look. Okay. Yeah, this is. Okay, we are going to solve this problem using inter-process communication. Okay, we have 5 rows. Okay, so if you don't have any controls, the 5 rows, 5 lorries, long lorries, or a queue of cars will crush together. Can you solve the problem? If they really have a crush, you cannot solve the problem. No one will try to release the rows that they occupy. Okay, or this is just a set of cars. Okay, then you cannot move, and it just stand there, can never make any progress forever. Okay, so that's why you have a control. And the solution to the control is our classic problem, dynamic philosopher. Okay, that system processes need the control. Last classic. Okay, last classic is a database problem, reader-writer problem. Okay, this problem emphasizes one thing: how to allow multiple readers to run, not just one reader and one writer. If we have a multiple writer, we get just only one guy can update the row. Okay, but how can I allow multiple readers at the same time? Okay, so I hope that we will finish before the classic problem tomorrow, and we'll start the classic problem next week. Okay, so see you tomorrow.